Welcome to the Belimo Knowledge Seminar. Today we continue our basic seminar on hydronics and valve selection in building technology. We will be sizing pressure-dependent valves together. My colleague Eugen Schubert once presented the basic hydronic circuits at the startup seminar. To start today's lecture, I will briefly repeat them. The throttle circuit. The volume flow is variable at the consumer and at the generator. In the case of the injection circuit with the two-way valve, the variability is at the generator and the constancy of the volume flow is at the consumer. With the mixing circuit, with a low-pressure manifold, we also have this combination. With the injection circuit with the three-way valve, both volume flows are constant. With the diverting circuit, the volume flow is constant at the generator and variable at the consumer. So that was a brief reminder of the basic circuits. The physical principles of valve sizing include the formula Q equals V multiplied by delta T multiplied by C multiplied by rho. Q stands for power. In heating technology, it is traditionally calculated in watts or kilowatts. V means the volumetric flow in cubic meter per hour. Delta T is the temperature spread, measured in Kelvin. C stands for the specific heat capacity and the Greek letter rho stands for the density of the medium. Another value we need for valve selection is the A value, as an example, of a heat exchanger. The A value describes the nonlinearity of the current output at the heat exchanger. For example, with an A value of 0.2, we have 50% flow with the valve half open, but 80% current output. However, we want to achieve approximate linearity. That is, at 50% flow rating we have 50% current output. We must therefore contrast the heating coil characteristic with a valve operating characteristic, that enables us to achieve a linear path characteristic at best. If we do not have an A value available to select the valve authority, as is the case here with a heating circuit with undefined consumers, a valve authority of 0.5 is often aimed for as a simplification. This means that half of the pressure loss in the control circuit is placed in the valve. Another value we need to choose the right valve is the KVS value. The KVS value corresponds to the volumetric flow in cubic meters per hour at a pressure loss of 1 bar, with the valve fully open. The KVS value is therefore the manufacturer's value, the catalog value that we manufacturers print. The KV value corresponds to the volumetric flow in cubic meters per hour at a pressure loss of 1 bar and a certain opening angle, or a certain stroke of the valve. The KV value is the value of the valve calculated during valve selection. Now, we have repeated all the necessary things for valve selection in fast forward. Now we finally come to the actual valve selection. Step 1. We need the nominal flow or volumetric flow in cubic meters per hour. For this purpose, we take the simplified formula, in this case to calculate the power of, for example, a cooling register. In general, this simplified basic formula is used for calculation. Next, we determine the pressure loss across the fully open valve. For the throttling circuit in this case, we aim to put half of the pressure loss into the valve. That means a valve authority of 0.5. Now we calculate the kV value of the valve with the help of the volumetric flow and the applied pressure loss. After determining the kV value, we look at the existing KVS values of a manufacturer, in this case those of the Belimo company, to see if we can find a suitable valve. Once we have determined two possible matching KVS values, we check the valve authority by recalculation. Then we make the decision which valve to use. Here, we naturally choose the valve that is closest to the desired valve authority. Using this example with realistic values, I would like to summarize the design once again. Step 1 shows that we have a cooling register with a value of 85 kilowatts. The temperatures of 6 degrees Celsius and 12 degrees Celsius respectively clearly indicate that this is a cooling line. This means that we have a delta T of 6 degrees Kelvin. We now enter these values into the formula and get a volume flow of 12.2 cubic meters per hour. In step 2, we calculate the pressure loss between supply and return at a valve authority of 0.5 and get 20 kilopascals, or 0.2 bar. In step 3, we can now calculate the kV value with the values we have just obtained. According to the formula shown, the result for the kV value is 27.3 cubic meters per hour. Now, I have looked in the catalogue and unfortunately I cannot find a valve with exactly this kV value. What there are, however, are valves with a kV value of 25 or 40 cubic meters per hour. By calculating the valve authority for these two valves we get a value of 0.54 in the first case and 0.31 in the second. Thus, it is clear that we choose the first valve found with a valve authority of 0.54, as this is very close to the desired value of 0.5. The valve with an authority of 0.31 cannot perform the control task sufficiently because the value is too low. Therefore, valve number 1 should clearly be selected. We therefore note the following statement. For the design of a pressure-dependent valve, the differential pressure over the variable flow line is decisive. We have summarized the 6 steps for designing the throttling circuit in table form here. We note that the differential pressure between flow and return has a significant influence on the design. We can now use the same steps to design the mixing circuit. It is important to note that the variable flow circuit includes the producer side. We recall that the mixing circuit is used where there are low-pressure manifolds. In the case of the injection circuit with the two-way valve, the differential pressure between the supply and return must also be used for the calculation. Due to the circuit layout, this is therefore the differential pressure that arises above the bypass. Of course, there is also a calculation tool that does the work for you for all these calculations. You can find this tool on the Belimo website. To do this, select the Product section. In the Valve section, you will find the Valve Sizing and Selection tool. We would be happy to send you the information from this presentation as a handout in compact form. Use the QR code to download the document in PDF format. The document includes the most common basic hydronic circuits with the required selection criteria and standard applications, along with general dimensioning and design instructions, summarized on one DIN A4 sheet. Thank you very much for your attention.